Okay, we'll go ahead and get started, and people join during the presentation, they can join at that point. So good afternoon, everyone, and thank you for joining today. My name is Erin McDonnell, and I'm the Associate Product Manager for Laser Interferometers here at Zygo, and today we're going to talk about overcoming some of the challenges of measuring plane parallel optics. If you have questions at any point, feel free to submit them via the question tab, and we'll answer some of them during the presentation. And I also have Mackenzie Massey and Rich Poltar on the line who will help to get back to you. So let's get started. So the problem we're talking about here is basically back surface interference. So does this look familiar? You're in the lab measuring your parts on your traditional mechanical phase shifting laser Fizeau, and you get a fringe pattern that looks something like this. Not sure what the issue is, but you hit measure, and instead of getting a nice clean surface map, you get something like this that has all sorts of discontinuities and dropout. That's not what anyone wants. The reason for this is that you're getting interference from the back surface. That's what the second fringe pattern is. This is caused by having a plane parallel optic. So, easiest solution, let's just not use plane parallel optics. Unfortunately, plane parallel optics really are everywhere. So plane parallel optics, by which I mean optics that contain zero wedge, are used in a number of different industries, including laser technology, semiconductor, medical technology, aerospace and defense applications, consumer electronics, and glass manufacturing. There are a number of advantages of using plane parallel optics. It gives you a minimum beam deviation if you're using them in transmission, like for cover glass or windows. It also gives a very predictable beam path, which is useful with items like beam splitters. They're also, if they're plane parallel, are usually weight balanced, which is useful in applications like hard drive disks or anything where the part actually needs to move. Quite simply, it's also easier to manufacture when both sides can be polished at the same time. So clearly plane parallel optics aren't going anywhere, so we have to figure out how to overcome these challenges. To do that, we want to start with why this is a problem. So let's go back to the basics of making a measurement. So here's our basic setup with our laser Fizeau interferometer. You have your interferometer here with a reference optic, what we call a transmission flat, or TF, aligned to the optical axis on the front. You then have your part under test, the one you want to measure, some distance L away, what we'll refer to as the cavity, that's also aligned to the optical axis of the interferometer. So you'll get an interference from this reference optic to the front surface of your part. Unfortunately, if this part is plane parallel, you're also going to get interference from the reference optic to the back surface of the part. That's when you get that second fringe pattern. So one solution is to do a transmitted wavefront measurement. In this configuration, you have the same reference optic on the front of your interferometer, just as you did before, but this time, instead of having your part under test aligned to the optical axis, you tilt the part under test off and instead have a return flat aligned to the optical axis of your interferometer so that you are transmitting through your part. This does get rid of the print through from various fringe patterns, but it only gives you a transmitted wavefront, or how the light deviates going through your part. It doesn't actually tell you what the front surface of your part looks like. So how does mechanical phase shifting work? With phase shifting interferometry, we have a mechanical phase shifter that physically moves the reference during a measurement, creating your interference signal. This length L changes over time, and that's how you get your surface data. Moving the reference is what modulates the interference signal. However, the problem with plane parallel surfaces and the back surface interference is the mechanical phase shifting can't separate these multiple fringe patterns. That's what causes the combination of dropout, discontinuities, and fringe print through that we see here. One common solution for this type of problem is to use a short coherent system to make measurements. These typically use an equal path interferometer with an extended broadband source. Short coherent systems typically have a very short, around 25 to 100 micron coherence band, usually a fixed distance from the interferometer. The way this works is with a traditional long coherent system, you get interference at any point in front of the interferometer. But with a short coherent system, you're only going to get an interference signal at a set distance, small window, at a certain point away from the interferometer during your coherence band. This type of measurement has many advantages, but at Zygo, we found that the best solution is to instead do phase shifting with wavelength. How this works is instead of moving the reference, we have a fixed cavity length, L, but we have a tunable source that moves the fringes and gives you your surface map. So in this case, tuning the light source modulates the interference signal, or in the case of plane parallel optics, multiple signals. So how does this work? Tunable laser source changes the wavelength slightly over the course of a measurement scan. There's a unique interference frequency for each pair of surfaces that allows these surfaces to be separated. This is because each fringe pattern moves at a different rate. It's a little hard to see, but check with the video here. These fringe patterns from the front of the optic to the front surface of the part with the reference optic move quickly. Whereas we'll see it again, this pattern here moves more slowly. That's the internal cavity. So how is this actually working? The fringe patterns for each surface can be separated using a Fourier analysis. The frequency that we just saw is converted to optical path length, which is unique for each cavity, cavity being what we define as the path between two surfaces. Cavities are then reported based on distance to make them easy to identify. In the interferometer setup that we have here, we have our reference optic, the transmission flat on the front of the interferometer, and then our parallel test part here. So this setup actually has three different cavities. We have one from the transmission flat to the front of the part, one from the transmission flat to the back of the part, and one from the front to back surface of the test part itself. This cavity length is approximately, in this scenario, about 100 millimeters, and then the test part about 5 millimeters. So the overall length, TF to the back surface, is about 105 millimeters. Easy to differentiate. So how does wavelength shifting and FTPSI actually work? Obviously, we only have one source, so everything should be shifting at the same time, right? The way this works is that longer cavities experience a larger phase change for the given wavelength shift. The graph here shows the phase modulation and how it's different for different cavity lengths for the same wavelength shift. In our setup here, and what's usually the case, our shortest cavity is between S2 and S3, which are the front and back surface of the part. That phase modulation gives us a very wide sine wave. For the longer cavities, with S1 to S2 or S1 to S3, so the transmission flat to the front and back surface of the part, the cavity is longer and gives us a tighter sine wave. So then what do we do with this? When you're making a multiple surface measurement on the MST, the fringe patterns for each of these surfaces modulates during the wavelength shift, as we saw in the earlier video. What the camera actually sees is the sum of these three fringe patterns, each shifting at a different rate. So in the dotted line, you can see the three sine waves we saw before, representing each of the three cavities. What they do is they sum into this darker black line, which looks like a kind of modified sine wave that's a signal from all the surfaces at once. These complex fringe patterns are then separated into individual fringe patterns, which convert to individual surface data using the Fourier-transform we discussed. This complex fringe pattern here is really no more than a set of horizontal fringes, which represent the front surface, a set of fringes at -45 degrees, which represent the back surface, and a set of fringes at +45 degrees, which represents the optical thickness variation. So how does this actually work? The Fourier transform converts the frequency space into physical distance. In a setup with both a transmission flat and a return flat, we have 4 contributing surfaces, which actually gives us 6 possible cavities. We have a cavity between the transmission flat to the front of the part, the transmission flat to the back of the part, the transmission flat to the return flat, the front of the part to the return flat, the back of the part to the return flat, and the front of the part to the back of the part. Each of these cavities is represented in our OPED spectrum based on their distance. The fastest peak here, so what moved the least, is the front of the part to the back of the part, so we get a spike at that distance. Each of these 6 peaks represents one of these cavities. So I know that's a lot of information, so we'll do some intermittent questions if we've had any submitted.
So we do have a couple questions. The first one is, what's the difference between measuring with a return flat and without one?
It's a really good question, and it's something we're going to get into more later in the talk, actually. But the biggest difference is if you're measuring the back surface directly or not. If you're using a return flat, then you're measuring from the back of the part to the return flat just in air. Without a return flat, you're measuring the back surface of the part with the transmission flat, so you actually are getting your data through the part, where it's not quite as clean.
And we have one more. How much does the wavelength shift, and do I need to worry about the index of refraction change?
Also a good question. So the wavelength shift is going to be dependent on your setup. The factors that it depends on are your kind of central wavelength and what your tuning rate, which is how fast we tune the laser. That's typically dependent on your cavity length. For a typical cavity, you're going to have less than a nanometer of tuning range or wavelength shift. So it's really not going to affect your index of refraction that much. If even that small shift is really a big issue for you in your setup, our metrology software, MX, actually does have the ability to enter a group index. So you can enter the refractive index at 2 slightly different wavelengths, and that'll let the software compensate for the change in index during the course of the measurement. All right, if those are the questions that we have for now, then I'll keep going. So we now know how an MST and measuring with FTPSI works, but what's the benefit of it? The biggest benefit of simultaneously measuring multiple surfaces is that the environment, even a really good one, is constantly changing. Individual surface measurements have no way to compensate for environmental change, while measuring simultaneously gives you the same environment for all surfaces so they can be compared directly. This is particularly important for thinner samples, which can deform easily. Additionally, you only need to set up and align once. This will increase your throughput, and it also avoids the inconsistency in positioning and aberrations that might be caused by flipping your part and having it be at a slightly different point in your field of view. Another big benefit of wavelength shifting is direct measurement. This goes to the question that was asked earlier. Wavelength shifting means that the starting point does not need to be at the interferometer. What we saw in the diagrams earlier is that with mechanical phase shifting, you're physically moving the reference. So that's your 0 point. But with wavelength shifting, your 0 point is one side of the cavity and then to the other end of your cavity. This means that the back surface can be measured directly if you use a reference flat. You can see a force surface, meaning TF, part, return flat, in this picture here. If you look, their back surface of the part to the return flat here is an air cavity only. This gives a direct back surface measurement, meaning that there's no effect from wedge and material inhomogeneity. So the measurement is just as reliable as if you physically flip the part. One of the biggest applications that we see with plane parallel optics are thinner glass measurements. Many applications, including cover glass, wafers, and hard drive disks, are currently driving towards much thinner optics, frequently less than 1 millimeter thick. Traditionally, these are very difficult to measure since the front and back surface peaks, as we saw in our OPD spectrum earlier, would be extremely close together. Zygo has been able to overcome this somewhat, and on our current MST, we can do a minimum optical thickness being the physical thickness of your part multiplied by the index of refraction of the material of 0.6 millimeters. The other thing you want to worry about with thinner glass is that it's much more susceptible to distortion. This makes taking measurements of optical thickness variation, physical thickness variation, and homogeneity much more important because it can be harder to get reliable measurements of the front and back surface. You're also going to want to key in on your fixturing for these thin samples. As we briefly mentioned earlier, thin glass samples are also very easily susceptible to environmental changes, making the simultaneous measurement even more important. I mean, think about it. If you have a thin piece of glass, say the thickness of your phone, the front of your phone or phone protector, you can probably even deform it with your fingers. Whereas if you have a piece of glass that's a couple inches thick, that's going to be a lot more stable. Along that line, you certainly want to take some fixturing considerations into account when you're measuring multiple surfaces. In order to measure multiple surfaces, a transmissive mount is required. Even if you have a transmissive mount, you want to ensure that your fixturing is not blocking your part. In this sample here, my mount is transmissive, but the diameter of that transmissive part of the mount is still smaller than my optic, so I'm cutting off the corners here, and I'm not going to be able to measure the full aperture of my part. The other biggest consideration for fixturing, especially with thinner samples, is to ensure that the part holder is not distorting the optic. In this picture here, you can see a part that's clearly being distorted by the indents that you can see at the 3 points where it was being supported. You can typically check for mounting stress on measured data by doing a higher order Zernike remove to see if you see these 3 points or a trefoil pattern, which is usually going to indicate some distortion. You want to try to hold your sample as lightly as possible without, of course, introducing additional vibration. You're also going to need to take into account your fixturing constraints in defining your cavity constraints, especially as to how close your fixturing allows you to get each different surface in your measurement setup. Setup configuration considerations certainly are important for multiple surface measurements on the MST. It is a familiar setup and alignment. You use the instrument exactly as you would a mechanical phase shifting tool, but you do have to make sure that the air gaps between the TF and the front of the part, the back of the part, and the return flat, and of course, the actual thickness of the part itself are all different lengths, so the peaks can be separated. You also do want to, as much as possible, minimize the cavity length in order to reduce your measurement time. The longer your cavity is, the longer your acquisition time will be, which will decrease your overall measurement throughput. Thankfully, our MX software, our current metrology software, is going to help you walk through a lot of that. MX will recommend the ideal cavity setup given the constraints you input. The ideal cavity is calculated taking into account your cavity constraints and minimizing harmonic interference with a preference towards a shorter cavity. MX software will also give a range of where to put your part. Here, saying putting the TF to the front of your part being somewhere between 156.2 millimeters and 189.3 millimeters, so that it makes setup a little bit easier and you don't have to try to position your part exact distance away. So these are all a lot of great benefits of making multiple surface measurements, but there's a lot of benefits of wavelength shifting even beyond that. One big one is beam expanders. Wavelength tuning acquisition scales extremely easily because you don't have to start your 0 point at the interferometer. At Zygo, our maximum aperture for mechanical phase shifting systems is 650 millimeters. This mechanical phase shifting beam expander size is limited by the weight and the phase shift distance that we physically have to move these large flats. I mean, think about it. A 24-inch piece of glass is going to weigh several hundred pounds. It's difficult to physically move and shift that optic. However, as we saw before, the MST doesn't need to move an optic. It keeps a static cavity length. So in that way, the MST enables our 600 millimeter and 800 millimeter aperture beam expanders. Another huge and underrated benefit of wavelength shifting is artifact reduction. It's fairly common to see central hotspots print through in the surface profile in a conventional piezointerferometer. That's what this center bullseye looks like. But since wavelength tuning can separate the interference, it ends up solving this problem. See, the bullseye basically disappears. This is because you're looking at a specific cavity length. What this bullseye is actually just an internal cavity. So as long as that internal cavity is a different length from the cavity that you're trying to measure, it's not going to show up in your MST data. So that's my presentation for today. I want to thank you all for attending. Any additional questions?
We do have a couple more questions.
Okay.
So the first one, are wavelength shifting tools visible only?
They're not. Obviously, our base configuration is at right around 633 nanometers in the visible, but we do also have options available at 1 micron and 1.55 microns.
Okay, and we have one more. You mentioned the changing environment. Mechanical phase shifting has ways to overcome the vibration. Is there an equivalent for wavelength shifting?
There is. So for on-axis measurements, we have a vibration robust method on the mechanical phase shifting tools called QPSI. We do have a wavelength shifting equivalent for cavities with one interference cycle. We also actually have recently released FTQPSI to give you the vibration robust performance on multiple surfaces and multiple surface measurements. Our truly vibration resistant measurement mode, our dynamic one, Dynaphase, actually doesn't use either mechanical phase shifting or wavelength shifting as its acquisition method. It's a carrier fringe, so does a single frame. So because of that, while we can certainly put Dynaphase onto any MST system, it's going to only work if there is one interference signal.
Those were all the questions.
All right, that's what we've got. Then I want to thank everybody once again for attending. If there are any other questions in the chat that are coming in later, then we will be sure to get back to you in the future. Certainly, if you have any additional questions or need more in-depth information about wavelength shifting in the MST, you can reach out to me or your sales or applications rep. Additionally, if you're interested in more in-depth technical discussion of FTPSI and the latest and greatest in wavelength shifting, one of our technology fellows, Les Deck, is giving a talk on that topic at the upcoming Optics and Photonics conference. So definitely check that out as well. So thanks for coming and have an excellent rest of your day.